Hey, what's up, guys? This is Sean here. So today's daily challenge problem number 234, palindrome linked list. Even though this one's an easy problem, the reason I want to talk about this one is because, this one has a few corner cases, especially if you want to solve this one with a O1 space complexity. So there are some, I think it's worth talking, basically. Okay, so the problem is pretty straightforward. Given like a linked list, and you return true if it is a palindrome, right? So I think everyone knows what palindrome is, right? So if you reverse that, then it'll be the same as the original one, right? So for example, this one is true, and the second one is false, because if you reverse this one, you have 2 and 1, right? Cool. So I mean, a naive approach is that, since it's a linked list, we can only start from the head and then going continue going to the right side. So a naive approach is that we're gonna maybe have like a array, right, or a string, whatever it is, and then while traversing the elements, we store that element into that array, and then in the end we simply reverse the array, and then we compare if the reverse array is equal to the original array, right? So that's gonna be O of n time n, but the time complexity will be O of n, right? Since we need an array to store all the nodes value. And so I want to talk about O1 time complexity. Sorry, the O1 space complexity. So in order to do that, we have to use like slow and fast pointer. So which means that, let's say we have basically we have like some 1, 2, 3, 4, 3 to 1, right? So let's say if this is the one, if we use the slow and fast pointer technique, and actually, so if you look at this one, for this one the number is odd, right? So which means we simply need to compare if these two parts are the same, right? And if we don't want to use the actual space, we have to somehow basically reverse either the front end or either the first half or the second half. In our case, I think we're going to reverse the second half. Sorry, the second half. I think you also reverse the first part. So after reversing that, we have 1, 2, 3, right? And then we simply just need to compare if this first half and second half are the same, right? And now the problem is that how can we find the starting point of the second half, right? Like I said, we need to use a slow and fast pointer. So basically, we have in a slow uh, pointer, it's increased by 1. So it jumps 1 step, and the fast it jumps by 2. So that when the fast reach the end of this node list, the slow will be pointing to here. Okay. But as you guys can see that, we have some corner cases here because, this is the odd case, right? And how about the even case? So we have 1, 2, 3. Let's say we have 4 and 4, and then 3 to 1, right? So for this one, actually the for the odd case, the starting point of second half is this 3 here. But the for the even case, the starting point of second half is here. Right? So basically we have to be careful when we write slow and fast logic to make sure the slow pointer will always pointing to this one here, and then for here this is going to be slow. So here we want to make sure it's pointing to here. Okay, so that's the first thing. And another corner case is like this one. So 1 and 2. So for 1 and 2, so what is the starting point of second half? It's here, right? So which means that we want our slow pointer stay at this one here, because basically the starting node of the second half will be the slow pointer dot next, and that will be the starting node of second half, and then we just need to use this node, the starting node, to reverse the second half. Right. All right, cool. So let's try to write that slow and fast logic. So we have slow and fast starting with head, right? And while fast is not empty and the fast dot next is not empty, we'll have like slow equals to slow dot next, and then fast equals to fast dot next, right? So and then we have second head. Second head equals to what? Let's assume we have this kind of reverse, and we have a slow dot next, and then we just need to compare that, right? But this, if you write this while loop in this way, there'll be a issue here, because if it is a 1 and 2 case, right? If it's a 1 and 2, fast and fast next, they're both not none. So which means that the slow will be moving forward, right? Which means that slow will be pointing to here, which is not what we want. We want slow to stay here, not moving forward, right? So how can we solve this one? For the corner case, only has two elements. We can simply fix this one by doing a fast dot next, and then fast dot next dot next. This will make sure the slow will stay at here. Let's verify this one with some like more examples here. Let's say we have 1, 2, 3, right? And then 4, 3, 2, 1, right? So let's only look at the fast pointer. So at the beginning, fast will jump to here, and here it will jump to here, right? And then here, how about here? So from here we have a fast dot next, which is 2. Fast dot next is 1. So it will also jump from here. Basically, the fast pointer will jump 3 times. So which means that after this one, the slow pointer will be at 1, 2, and 3. So this will be the slow pointer, right? And the slow pointer dot next is the starting point of the second half, so which means the odd case works. So let's try that even case, right? 4, 4, 3, 2, 1. So for the even case again, right? So the fast jump to here, 1, 2, and 3, right? So when the and the slow pointer will also point to 1, 2, and 3, which is here, right? And then slow dot next is also the starting point of the second half. So which means it also works. Actually, you know what? Actually, I thought about this a little bit more. Actually, if we use the previously like fast and fast dot next, and we can simply change this slow dot next to slow, because if we use the fast and the fast dot next, actually the slow pointer will be pointing to the starting point of the second half, right? Because again, so if we use this one, the slow will be pointing to here, and here the slow, sorry, I think I take that back. Actually, this one will not work. Basically, no. If we use this one, I mean, for this even case, for this odd case, the slow will still be pointing to here. So basically, we're trying to reverse here, trying to reverse this starting from 4 here, because this one will still jump to 3 times, and here basically we'll have like a 1, 2, 3, 4 in the end, right? Which might also be okay, because even though this one, even though it's for the odd case, if we use this one, the slow pointer is not pointing to exactly the place where we want to do the reverse. But even though we reverse a little bit more, one more element, but this one will not affect the final answer because, in the end, while we're comparing this 1, 2, 3 and 1, 2, 3, 4, we will stop at 3 here. So we don't care about 4. So this one will also work actually. So I think so. Yeah. And for the even case, right, if we follow this one, we're gonna have like 1, 2, 3, and then here, right? So as you guys can see, when the fast pointer is here, the fast and the fast next, they're both true. So which means the fast pointer will move one step forward, which means the slow pointer, instead of pointing to here, it will point into here, which is exactly what we need, right? And then we do a swap, reverse. So, okay, basically either way works. You can either use a fast dot next and the fast dot next, and then you use the slow dot next, or you can use the fast and fast next and then use slow here. Okay, because later on, when we do the comparison here, we're gonna do a while hat, right, and then the second hat, right, and then we'll compare that. Basically, if the hat dot value does not equal to the second hat dot value, we'll simply return false. Right? Otherwise, we'll move this hat forward. Right? Otherwise, we simply return true in the end. But how about this one? Actually, I know you have some questions. Let's say we have 1, 2, 3, 1, 2, 3, 4, 3, 2, 1, right? Mm, when we try to compare these things here, right? Basically, we have 1, 2, 3, 4, and when we reverse the second half, right? So from 4 here, it'll become 1, 2, 3, and 4, right? That's the second half because from second half here is 1, 2, 3, 4, and when we try to compare the hat, this hat here, what's going to be the hat? So it will also be 1, 2, 3, and 4 actually, right? So for the first half, it's still 1, 2, 3, 4, because we never change the next pointer out of 3, so which means that 3 dot next still pointing to 4, and this while loop stops when the second hat equals to empty, equals to none, which is the next one is none here, right? It's none. That's why even though with this kind of like reverse, even though it's reverse a little more, also reverse this 4 here, but it will not affect the final answer because the 4, it's common. Basically the 4 is the same in both the first half and second half, right? And so this one also works if the slow point, if the second half is at its correct position, which is 3 here. If that's the case, of course it will also work because 1, 2, 3 is also works with 1, 2, 3. Okay, so now the only remaining part is the reverse, right? That's going to be a very standard method, which is going to be a reverse. Going to have a node, right? So for the reverse, we always need to have a pre, right? And then we have a current equals to node, and then we have a while current, right? So we need a temporary node to store the current dot next, and then we have current dot next equals to pre, right? And then the next one is the pre equals to current, and then the current equals to temp, and then in the end we return the pre. Yep, I think that's it, right? So if I run the code here, okay, this one accepted, and let's submit. Cool. So this one works, right? And let's just give it a try. Let's try the other one, right? Fast.next and fast.next.next, right? So if that's the case, we have to use slow.next, right? So this one should also work. Yeah, cool. Yeah, I think that's it, right? I mean, obviously this one is like O of n time complexity and O of one space complexity because we're not using any additional storage, only by changing the pointers, right, of each node. Cool. I think I'll stop here and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.